Hi everyone. So we're at part 2 of our GIS 305 week 5 lecture. It's part 2 of 2. So this week I'll say we have shorter lectures and a pretty substantial assignment with much detailed clicking and specification work in QGIS. So I will now go to our presentation and get started with part 2. Accuracy assessment, and this is how to assess the quality of an image classification. How accurate would an image classification be? So, it's again part of the digital image processing sequence. Here, accuracy assessment is very important to see if the information we've extracted from the image is actually true or not. Is it valid information? Very important, accuracy assessment in remote sensing, any kind of remote sensing project. So, what do we mean by accuracy assessment? Well, it's a qualitative measure of categorical accuracy of a thematic map. It's based on a comparison of um, the image values, that is the thematic map, versus some kind of a sample, uh, field sample, or another kind of map source that is going to serve as reference data. So we need reference data to do accuracy assessment. That's a key point. And what our reference data set can be, well, it's some kind of individual data set for validation purposes. Your validation samples can be gathered directly from image interpretation, and this is quite common, or from other maps, such as topographic maps with categories that are similar to your classification, or from aerial photographs that are easier to interpret than some of the coarser um, remote sensing images, or Google Earth, Bing Maps, or in many cases, in classic remote sensing cases, you'll have field samples with GPS coordinates that you can associate with a given pixel in your image. So, an important point here, very important, is you cannot use your training samples. The training samples that you've entered into or you've contributed to the algorithm or supplied, I should say, to the algorithm, they will have been used to calibrate your model, your classification models. So if you use some of your training samples as reference samples, you're going to have a artificially high accuracy because simply you're using you're using as reference data the data that was used to train your model. So one big thing not to do. And the second thing to consider is how accurate is the reference data actually? Is the reference data telling you really what is on the ground and what the satellite or the remote sensing image sees? Okay, so sampling matters. It needs to be representative and offer samples of all your categories, ideally of every possible category that you can find in your image. Also, because images vary spectrally, the spectral data can vary through space, it's important for the data to be, your reference data to be well distributed over your area of interest. And finally, there's a lot of rules of thumb for sample size, but it will depend on the number of map categories. So for instance, there's one rule of thumb that says that you should have at least 10 times more samples than you have categories. And it'll also depend on the level of detail of your accuracy assessment, how detailed you want that accuracy assessment to be. But as a rule of thumb, and that's what we'll just run with here, is that there should be at least 30 observations for each class to have a reasonable accuracy. So keep in mind that 30 samples per class is probably a good idea. Okay. So different sampling strategies are possible: random sampling, stratified sampling, and systematic sampling. So random sampling is what it is. It's essentially you're going to obtain samples for a random selection of pixels in your image. So that essentially you're expected to have easy access to any place in your image, any physical place that is within your study area, and that's typically very difficult and expensive, so that's not often used, like actual random sampling, um, unless you're using some kind of GIS as a reference data set. But typically, for remote sensing, you'll have some kind of stratified random sampling. So it's stratified random sampling is an approach by which there's first a judgment call that is made as to the areas that are deemed accessible, um, the sites that might contribute to a sufficient range of um, access points to all the classes of interest that you have in your class hierarchy, for instance, and then within those areas you apply some kind of a random sampling um, technique, and that makes it a lot more easy logistically and a lot less expensive. So that's a common um, approach that is used in remote sensing, stratified random sampling. Or then you can have also systematic sampling. So that's basically applying some kind of a grid or transects or some kind of a system that is very regular. Again, it's often not very practical, but for small areas or for given purposes, it can be a strategy that will work. Systematic sampling. So just keep in mind these three different ways of approaching the collection of field samples or image samples. Okay, and once you have your reference data, your samples, your reference samples, not your training samples, you can produce what is called an error matrix, or often called also a confusion matrix. And this is a table, essentially, where each and every one of your reference samples is run and compared to what the classification, the classified image says it found for that given location. So if, for instance, I have 53 samples for my class A, and I find out that the classification of the image, the classified image, agrees that 35 of those are actually, yes, they're, I've classified them as A, then here I'm going to, so there's a partial agreement. There's a number of these reference points where I'm expecting the classification to have found class A, but it actually found class B, C, or D. So here there's only a proportion of my class A samples that were correctly classified. So that's, and you can do this for every class, obviously, and we're going to look at this in a bit more detail in the following slides. But essentially what the error matrix does is it calculates, it compares the location and the category of each ground truth pixel with the corresponding location and category in the classified image. So each column here is your reference data or your ground truth category, and each row is information obtained from the classified image. So your overall accuracy for your classification will be calculated simply by looking at all the correctly classified samples, summing them up. You have 163 here, and so pardon me, 163 is the total of all your samples, reference samples, and you'll see that here you have the sum of the yellows is 86, and 86 out of your total 163 is 53% overall accuracy. Now here there's important lingo to understand, and that's the producer's accuracy versus the user's accuracy. Um, the producer's accuracy is from the standpoint of the person who produced the map. You're looking at how many of my reference samples have been correctly classified. Here I have 35 out of 53. We'll look at this more closely again in further slides, but that's your producer's accuracy. From the user's perspective, if I'm using the map, I'm going to say that, oh, I'm looking at class A. What are the chances that class A is correctly classified? Well, it turns out, there's another number of samples that were classified as class A. So as a user, I can only expect my classification for A to be as good as 35 out of 61. So that's your user's accuracy. And those numbers are as follows. Oh, well, we'll touch on them at the following slide. We'll also introduce a bit of language here. Omission error and commission error. So an omission error, it refers to the number of pixels that are incorrectly or erroneously excluded from a category. So it's all your false negatives. That's your omission. You've omitted pixels, so these are negatives, and they're false negatives, so it's an error. It's an omission error. A commission error is when you've committed pixels, you've classified pixels, again, erroneously into a category when they should not have been in that category. So those are false positives. So that omission error and commission error, you'll see how they fit in our error metrics soon. And then individual class error, well, that's essentially the error levels reported for an individual category. We've talked about the overall map error. And this is essentially the summary of what we've talked about so far. The error of commission and the user accuracy are these numbers here. So my user accuracy is 57% for class A, because I can only say that about 35 out of 61 of these classes of classified areas are correctly classified. So as a map user, I can only say it's 57% reliable. And that's the complement of the error of commission. So 43 and 57%, total 100%. So that's your error of commission is this 43%. So I've committed pixels to a class when I shouldn't have, to the order of 43%, pardon me. And the flip side of that is the error of omission and the producer's accuracy. The producer will say, well, I've used so many reference samples, and I've got 66% of my class A correctly classified, 28% of my class B, 59 of my class C, and 29 of my class D. Those are my producer accuracies. But there's a number of my reference samples that I've not classified correctly, so they've been omitted from this class to the order of 34, 72, 41, and 71%. So this is language here that you need to master. It's a little hard to wrap your head around, but again, things to learn about error matrices, error matrices and how to interpret them. And again, the overall accuracy is the sum of our yellow boxes here divided by the entire group of our reference points, 53% in this case. There's another metric that is that sums up the accuracy of a given classification, and that is the kappa coefficient. It's a statistical product. Again, it's a comparison of the agreement between the measured and the measured our measured success levels, and how they would compare to what you would expect from an absolute random assignment of your pixels to different classes. And these values are just general categories, but when you have a kappa coefficient of more than 0.8, you'll see that we'll say that you have a strong agreement. Whenever it's below 0.4, you'll say it's a poor agreement. It ranges between -1 and 1. Um, so yeah, that's something you can read about. We won't dive into it more for the purpose of this lecture. But if you want to read a bit more about error matrices and how to interpret them, you've got a couple links here that are good ones. And as a quick summary of the language that we should remember here for accuracy assessment. So accuracy assessment absolutely requires reference data or some kind of ground truth. That's a key point. Your overall accuracy can be given by just your percentage of accurate classifications, or kappa statistics. It's another way of publishing your results. You remember to know what the producer's accuracy is and the user's accuracy. They're two different things, and how they relate to errors of commission and omission. And this is your reading for this week, and that is the end of part 2.